Module 25, Lecture A, Neighborhood Manifolds. By the end of this lecture, you will be able to explain the manifold assumption through visual examples, apply Isomap and LLE family methods to nonlinear datasets, and analyze neighborhood construction, solver choices, and out-of-sample transformation behavior. Manifold intuition. Manifold assumption. The manifold assumption says that high-dimensional data may have a simpler underlying structure because its real variation often lies on a lower dimensional surface. For example, images with thousands of pixels may be driven by only a few factors, such as head position or lighting. This idea helps data analysis focus on the essential patterns rather than the apparent complexity of many features. High-dimensional data may look complex, but it often lies near a simpler underlying shape rather than filling the whole space evenly. To reduce dimensions without losing important structure, we need to follow that shape instead of relying only on straight-line distances. For example, images of a rotating chair can form a simple path in pixel space, showing that only a few factors drive most of the variation. The manifold assumption says that data may lie on a curved, lower-dimensional surface within a larger space, so meaningful closeness should be measured along that surface rather than through the surrounding space. Manifold learning uses this idea to preserve local neighborhoods and reveal the data's underlying structure. Even when a dataset does not form a clear manifold, the assumption helps focus on geometry and distinguish real patterns from measurement noise. Isomap intuition. Isomap is a dimensionality reduction method that preserves distances along the data's curved surface rather than straight through the surrounding space. Based on the manifold assumption, it treats high-dimensional data as lying on a lower-dimensional surface. Its goal is to recover the geometry of that surface as if it were unfolded, using shortest paths along the data manifold as the meaningful distances. In a Swiss roll shape, straight-line distance can make points on different layers look close, even though they are far apart along the surface. This can confuse dimensionality reduction methods by treating distant regions as neighbors. Isomap avoids this by building a graph of local neighbors on the surface, then estimating distance by traveling through that graph, like following roads instead of measuring directly across space. Isomap helps reveal simple underlying patterns hidden inside high-dimensional data. For example, many pixels in face images may mainly reflect a few changes, such as head pose and lighting. By preserving meaningful paths through the data, Isomap creates a lower dimensional map that better represents the true structure rather than just surface-level closeness. Python code, Isomap intuition. This example shows Isomap applied to a Swiss roll dataset. Isomap keeps distances measured along the curved surface, allowing the data to be unfolded into a two-dimensional map. We import key Python libraries for numerical computing, visualization, and machine learning. NumPy handles efficient numerical operations, Matplotlib creates visualizations, and Scikit-Learn provides tools for manifold learning. We also use the Swiss roll dataset generator to create three-dimensional test data, and Isomap to reduce nonlinear high-dimensional data while preserving its underlying geometry. We create a synthetic Swiss roll dataset using Scikit-Learn's make_Swiss_roll function. It generates 900 three-dimensional points with a small amount of noise, and a fixed random state makes the results reproducible. The output includes the point coordinates and each point's position along the roll, providing the data needed to show how Isomap can unfold the shape into two dimensions. Before running Isomap, the code verifies that the data has the expected shape, 900 points with 3 coordinates each. If the shape is wrong, it raises an error to stop the process. This check helps ensure the data is valid for the Isomap transformation. We create an Isomap model that uses 10 nearest neighbors and reduces the data to 2 dimensions. Applying its fit transform method to the three-dimensional points lets Isomap estimate shortest paths along the manifold and map the data into a flatter two-dimensional form. This effectively unfolds the Swiss roll while preserving its underlying geometry. The code first reports the Scikit-Learn version to support reproducibility. It then summarizes the transformation. 900 points from three-dimensional space are mapped into two dimensions. The plot colors show each point's position along the original rolled sheet, helping reveal how the data's underlying geometry appears in the two-dimensional map. A new Matplotlib figure and axis are created to prepare the plotting area. The axis then displays a scatter plot of the two Isomap dimensions, with each point colored by its original position on the Swiss roll, using the Viridis color map. The points are sized to remain clearly visible. The plot is titled to show that Isomap unfolds the Swiss roll manifold, giving the visualization clear context. The axes are labeled as the first and second Isomap coordinates, indicating the two-dimensional embedding produced by the transformation. A color bar linked to the scatter plot shows position along the original rolled sheet, helping connect the three-dimensional data to its flattened representation. Finally, we use Matplotlib's show function to display the plot. This makes the two-dimensional Isomap view of the Swiss roll visible on the screen, so it can be examined and analyzed. This example uses Isomap to reduce a three-dimensional Swiss roll dataset into two dimensions. Isomap preserves distances along the curved surface, so the rolled shape is unfolded into a simpler map while keeping its main geometric structure. The resulting scatterplot colors points by their original position on the roll, showing how the method reveals the underlying manifold. Geodesic neighborhoods. A geodesic neighborhood measures closeness by the shortest path along a curved surface, not by straight-line distance through the surrounding space. On a manifold, points that look close in flat coordinates may be far apart when you follow the surface itself. This idea is important because data on a manifold should be understood through its underlying curved structure. Geodesic neighborhoods measure closeness by how points can move along a manifold, not just by their straight-line distance in the surrounding space. This matters when data is folded or projected, such as images of rotating objects or sensor readings, where points that look close may represent very different states. By preserving local movement, geodesic neighborhoods capture small, realistic changes and avoid misleading shortcuts. Geodesic neighborhoods connect each data point to nearby points in the same local region of a manifold, then use those links to trace longer paths. This works because small parts of complex data often behave as if they are flat. A good neighborhood graph follows the data's true shape and avoids false shortcuts, while a poor one can disconnect related points or link unrelated regions. Python code. Geodesic neighborhoods. This script contrasts straight-line distance with distance along a manifold. Using a crescent shape, it shows how Euclidean distance can create misleading shortcuts, while geodesic neighborhoods better reflect the shape's true structure. We import key tools for working with and analyzing a synthetic dataset. NumPy supports numerical operations, Matplotlib creates visualizations, and Scikit-Learn provides functions to generate crescent-shaped moon data, build a nearest neighbor graph, and compute distances between pairs of points. Together, these imports prepare us to explore local relationships and distance measures in the data. We generate a small, nonlinear dataset using Scikit-Learn's makeMoons function, which creates two interleaving half-circles. The dataset contains 160 samples with slight noise added to make it more realistic, and a fixed random state ensures the same result each time. Finally, we verify that the data has 160 points with two features, raising an error if the shape is not as expected. We first isolate the points belonging to one crescent by by selecting those with label 0. Within that group, the leftmost point becomes the starting point, and the rightmost point becomes the ending point. These two opposite endpoints provide a basis for comparing distances across the dataset. We build a local connection graph by linking each point to its 6 nearest neighbors using distance. The graph is made bidirectional by matching each connection with its reverse. We also compute all pairwise Euclidean distances, which will support later shortest path calculations through the graph. The setup begins by counting the points in the dataset and creating tracking arrays for the pathfinding process. One array records which points have been visited. Another stores the current shortest known distances, and a third keeps the previous point needed to reconstruct each path. All distances start as unknown, except the starting point, whose distance is set to 0. The algorithm repeatedly chooses the unvisited point with the smallest known geodesic distance. If no reachable point remains, it stops. Otherwise, it marks that point as visited, checks its connected neighbors, and updates any neighbor whose distance can be shortened through the current point, also recording the current point as its predecessor. To reconstruct the path, begin at the endpoint and work backward using the stored predecessor for each node. Continue until the start point is reached, adding each predecessor to the path. If a missing predecessor is found, the graph is disconnected and an error is raised. Finally, reverse the collected path so it runs in the correct order from start to end. The code compares 2 ways to measure distance between selected points. It first reports the straight line Euclidean distance, then the geodesic distance, which follows the shortest route through the neighborhood graph. It also prints how many local connections are used along that path. The plot shows all data points, colored by their labels, then compares 2 ways of connecting a selected pair of points. A dashed black line marks the direct Euclidean shortcut, while a thicker gold line shows the geodesic path through the neighborhood graph. The 2 selected points are highlighted in lime with black edges, so they stand out as the start and end points. The plot is titled to emphasize that geodesic neighborhoods avoid shortcuts. Its axes label the 2 feature dimensions, and a legend identifies the Euclidean shortcut and the geodesic path. The visualization is then displayed to compare these paths clearly. This script compares straight-line distance with geodesic distance on a noisy crescent-shaped dataset. It chooses 2 points on the same crescent, builds a local neighborhood graph using nearby points, and finds the shortest path through that graph. The result shows that the direct Euclidean distance can cut across empty space, while the geodesic path follows the curved structure more faithfully. This demonstrates why local connections can give a better sense of distance in nonlinear data. LLE family. Local linear structure. Locally linear embedding, or LLE, reduces high-dimensional data by assuming that small neighborhoods behave like flat, linear patches. It represents each point using its nearby neighbors, preserving these local relationships in a lower dimensional space. This makes it useful for data such as images or sensor readings, where complex observations may depend on fewer underlying factors. Locally linear embedding preserves how each data point can be reconstructed from its nearby neighbors. It first finds weights that describe each point as a combination of close points, capturing local structure rather than overall distances. Then it builds a lower dimensional representation that keeps these same local relationships, helping reveal complex manifold structure without requiring an explicit formula for it. Locally linear embedding depends on choosing neighborhoods that capture the data's true local structure. Neighborhoods that are too small can be noisy, while neighborhoods that are too large may connect points that are close in the original space but far apart on the manifold. With well-chosen neighborhoods and dense enough sampling, LLE can reveal meaningful low-dimensional coordinates that reflect the data's intrinsic structure. Python code. Local linear structure. Locally linear embedding shows that small neighborhoods on a curved manifold can often be treated as merely linear. By comparing these local neighborhoods, LLE preserves their relationships while unfolding the broader curved structure into a lower dimensional representation. We import key Python libraries for numerical work, visualization, and machine learning. NumPy supports numerical operations, Matplotlib handles plotting, and Scikit-Learn provides tools to create an S-curve dataset, reduce its dimensions with locally linear embedding, and find nearby data points using nearest neighbors. We create a synthetic, three-dimensional S-curve dataset using Scikit-Learn's S-curve generator. It produces 700 slightly noisy samples with a fixed random seed for reproducibility. The output includes the three-dimensional points and a color value for each point, which helps show their order along the curve. Before modeling, the code confirms that the dataset has the expected structure, 700 samples with 3 coordinates each. If the shape is incorrect, it raises an error, so the problem can be fixed before later processing. The locally linear embedding model is configured to reduce the data to 2 dimensions while preserving local linear relationships. It uses 12 nearby points to estimate each point's local structure, applies the standard method, and lets the algorithm automatically choose the most efficient eigensolver for the data. Locally linear embedding reduces 3-dimensional points into a 2-dimensional representation. It preserves local relationships between nearby points, helping reveal the structure of data that lies on a curved manifold. This makes complex data easier to visualize while keeping important neighborhood patterns intact. To assess local reconstruction quality, a nearest neighbors model is built, using one extra neighbor so each point can include itself. The model is fitted to the 3-dimensional points, then used to find each point's nearby points, along with their distances and positions in the dataset. These neighbor relationships show how closely each point is reconstructed within its local area. To find the average distance to neighboring points, ignore each point's distance to itself and average the remaining neighbor distances. Then use the locally linear embedding model's reconstruction error to assess how well local linear relationships are preserved after reducing the data to a lower dimensional space. The code reports key details for a locally linear embedding analysis on a synthetic S-curve dataset with 700 points. It prints the Scikit-Learn version for reproducibility, uses 12 neighbors to define each local neighborhood, and summarizes the average nearest neighbor spacing. It also reports the reconstruction error, which indicates how well the lower dimensional embedding preserves the dataset's local linear structure. A plot is prepared by creating a figure and axis, then displaying the 2-dimensional LLE embedding as a scatter plot. Each point uses the first 2 embedding coordinates for its position and is colored according to its original location on the S-curve, with a viridis gradient and a visible point size. The plot visualizes the result of locally linear embedding, showing how LLE preserves local linear neighborhoods. Its 2 axes represent the first and second LLE coordinates, while the color bar indicates position along the S-curve. Displaying the plot lets us inspect how well the transformation captures the manifold structure. This script shows how locally linear embedding can unfold a curved S-curve dataset into 2 dimensions. It creates 700 3-dimensional points, applies the method using 12 neighbors to preserve local structure, and reports basic evaluation measures such as neighbor distance and reconstruction error. The final visualization colors points by their original position on the curve, showing that the reduced embedding keeps nearby points together while revealing the manifold's unfolded shape. Modified LLE. Modified locally linear embedding improves standard LLE by making low-dimensional embeddings more stable when data is noisy or unevenly sampled. While standard LLE reconstructs each point from its nearest neighbors, Its weights can be sensitive to small changes in complex datasets. Modified LLE uses a richer local reconstruction to better preserve the manifold structure and produce more reliable embeddings. Modified LLE improves on standard LLE by recognizing that local neighborhoods can vary in several important directions at once. It uses extra local information to reduce dependence on unstable reconstruction weights, especially when many neighbors are used relative to the manifold's true dimension. This helps capture variations such as stroke thickness and slant in handwritten digits, producing a smoother low-dimensional embedding where nearby points better reflect real similarity. Modified LLE works best on nonlinear data when the neighborhood size is chosen carefully, because it treats small parts of the manifold as roughly linear. Too small a neighborhood can capture noise, while too large a one can blur the true structure. By improving stability over the original method, modified LLE can help reveal meaningful geometric patterns in high-dimensional data, though pre-processing and careful parameter selection are still important. Python code, modified LLE. This example compares original and modified locally linear embedding on a noisy Swiss roll. It highlights how each method captures nonlinear neighborhood structure and preserves local geometry in the resulting embedding. We import the main tools needed for this manifold learning example: NumPy for numerical arrays, Matplotlib for plotting, and Scikit-Learn for machine learning utilities. From Scikit-Learn, we use the Swiss roll dataset generator to create synthetic data, locally linear embedding to reduce its dimensionality while preserving local structure, and a standard scaler to normalize features so distance calculations are balanced. We create a Swiss roll dataset, a three-dimensional spiral shape, using Scikit-Learn's Swiss roll generator. It contains 700 slightly noisy samples with a fixed random seed for reproducible results. The generator returns the three-dimensional point coordinates and each point's position along the spiral, giving a nonlinear dataset well suited for testing dimensionality reduction methods, such as locally linear embedding. We use Scikit-Learn's standard scaler to put all features on the same scale. It standardizes the data so each feature has a mean of 0 and a standard deviation of 1, helping distance-based methods like locally linear embedding compare points fairly across coordinates. Before fitting the neighborhood embeddings, the code confirms that the scaled data has the expected shape, 700 samples with 3 coordinates each. If the shape is different, it raises an error to stop the process. This check helps ensure the data is properly structured before the embedding analysis begins. We configure Scikit-Learn's locally linear embedding to reduce the data to 2 dimensions for visualization. It uses 18 nearest neighbors to capture local structure, applies the modified method to better preserve local geometry, and sets a random state so results are reproducible. We apply modified locally linear embedding to the scaled data to reduce it to 2 coordinates per point. This creates a compact representation that preserves local neighborhood relationships and the data's underlying manifold structure. The result makes complex high-dimensional data easier to visualize while keeping its essential geometry. The process begins by noting the Scikit-Learn version to support compatibility and reproducibility. The dataset is a noisy Swiss roll with 700 samples, and dimensionality reduction is performed using modified locally linear embedding with 18 nearest neighbors. A Matplotlib figure and axis are created to prepare the plotting area. The scatterplot then displays the 2-dimensional embedding using the first 2 embedding coordinates for each point. Points are colored by their original position on the Swiss roll with the Viridis color gradient, making the structure easier to distinguish. The plot is titled to show that it displays a modified LLE embedding of a noisy Swiss roll. The horizontal and vertical axes are labeled as the first and second modified LLE coordinates, and a color bar indicates each point's position along the original roll. Finally, we use the pyplot show function to display the completed plot. This reveals the two-dimensional modified locally linear embedding of the noisy Swiss roll, showing how the algorithm captures the underlying manifold structure. This script uses modified locally linear embedding to visualize a noisy three-dimensional Swiss roll in 2 dimensions. After scaling the data, the method uses 18 nearest neighbors to preserve local structure more effectively than standard LLE. The final colored plot shows how well the embedding maintains the Swiss roll's intrinsic geometry. Hessian Eigenmapping. Hessian Eigenmapping is a manifold learning method related to locally linear embedding that finds low-dimensional structure by preserving smooth curvature. Instead of relying mainly on neighbor weights, it minimizes local bending, so coordinate functions vary smoothly across the manifold. This helps reveal underlying variables in high-dimensional data, such as the rotation angle in images of a rotating object. Hessian Eigenmapping finds low-dimensional coordinates for data on a manifold by studying small neighborhoods around each point. It estimates local tangent directions, then uses second-order bending information to capture the manifold's underlying structure more accurately than purely linear methods. The goal is a smooth embedding where nearby points stay close and gradual changes, such as related poses in motion capture data, are represented naturally. Hessian Eigenmapping can reveal a manifold's smooth coordinate structure, but it is sensitive to data quality and neighborhood choice. Neighborhoods must contain enough nearby points to estimate local curvature without becoming so large that they no longer represent a nearly flat patch. The method works best on smooth, well-sampled manifolds, while sparse data, outliers, or sharply bending regions can make the embedding noisy or distorted. Python code. Hessian Eigenmapping. This script applies Hessian Eigenmapping to curved data and compares the original height values with the learned coordinates. The goal is to show that the method can recover a smooth parameter of the underlying manifold. The script imports key Python tools for numerical computing, visualization, and machine learning. It uses NumPy for calculations, Matplotlib for plotting, and Scikit-Learn for data analysis. From Scikit-Learn, it brings in a function to create a three-dimensional S-shaped dataset and a locally linear embedding method used here for Hessian Eigenmapping, which helps reveal the structure of nonlinear data. We generate a small nonlinear dataset using Scikit-Learn's S-curve generator, which creates an S-shaped manifold in 3 dimensions. The data includes 700 samples with slight noise to mimic real-world imperfections, and a fixed random seed makes the result reproducible. The generator also provides each point's true position along the curve, giving a known structure for testing Hessian Eigenmapping. Before fitting the embedding model, the code confirms that the generated data has the expected dimensions, 700 samples with 3 features each. If the shape is incorrect, it raises an error to stop the process. This check ensures the data is properly structured before embedding begins. We configure a locally linear embedding model for Hessian Eigenmapping to reduce the data to 2 dimensions while preserving its main manifold structure. The model uses 18 neighbors to estimate local curvature, applies the Hessian method to capture that curvature, and lets the algorithm automatically choose the eigensolver. We fit a Hessian locally linear embedding model to the data, so it can learn the data's local manifold structure using nearby points. The fitted model then reduces the original 3-dimensional data to 2 dimensions, preserving the key intrinsic geometry for easier visualization. The script checks key outputs to confirm the embedding process is working correctly. It reports the Scikit-Learn version, verifies that the input data has 700 samples with 3 features, and confirms that the Hessian embedding reduces the data to 2 dimensions. Create a plotting canvas with a 7 by 5 inch figure. Then make a scatter plot from the 2 columns of the embedding, which give the learned 2-dimensional coordinates. Color each point by its original position along the S-curve using the Viridis color map, and use moderately sized points so the pattern is easy to see. The plot is titled to show that it visualizes Hessian Eigenmapping of an S-curve manifold. The x-axis and y-axis are labeled as the first and second learned coordinates, making clear that they represent the 2 dimensions of the embedded data. These labels help viewers interpret the transformed data more easily. A color bar is added to connect the scatter plot colors with each point's original position along the S-curve. Labeling the color bar makes this meaning clear, helping us interpret how the Hessian Eigenmapping embedding reflects the original data structure. The plot is then displayed for visual inspection. This example applies Hessian Eigenmapping to an S-curve dataset using Scikit-Learn's locally linear embedding method. It reduces noisy 3-dimensional data to 2 dimensions while using nearby points to capture the curve's local structure. The resulting color-coded plot shows how the embedding preserves the original progression along the manifold, illustrating how manifold learning can reveal the intrinsic geometry of complex data. Manifold practice. Local tangent alignment. Local tangent alignment studies curved manifolds by treating small neighborhoods around each data point as nearly flat. It estimates local coordinate systems from nearby points, then aligns them to form a consistent lower dimensional representation. This is useful for smooth high-dimensional data, such as changing object images or robot sensor readings, where the important variation can often be described by fewer local directions. Local tangent alignment depends heavily on choosing appropriate neighborhoods, because tangent estimates come from the selected nearby points. Neighborhoods that are too small can be noisy and unstable, while neighborhoods that are too large may mix different parts of a curved manifold and distort the estimate. This is especially important when the manifold folds close together in the original data space, so raw proximity may not mean true similarity. Careful choices of neighborhood size, distance metric, and noise handling are therefore essential for capturing the manifold's local geometry. After estimating local tangent spaces, the algorithm aligns these small patches into one shared coordinate system, while preserving neighborhood relationships. This can reveal a coherent low-dimensional structure, but uneven sampling, boundaries, or branching shapes can distort the result. Practitioners should check the neighborhood graph and embedding carefully, since local tangent alignment depends on assumptions about smooth, consistent data. Python code, local tangent alignment. This example shows how local tangent alignment depends on neighborhood size. Changing the neighborhood changes each tangent estimate, revealing which neighborhoods give stable results and which can be misleading. We import key tools for working with a manifold learning example: NumPy for numerical arrays, Matplotlib for plotting, a Scikit-Learn function that creates a 3-dimensional S-curve dataset, and a nearest neighbors tool for finding nearby points. Together, these imports support generating the data, visualizing it, and estimating local tangent directions on the manifold. We generate a small 3-dimensional S-shaped dataset using Scikit-Learn's make S-curve function to represent a nonlinear manifold. The data includes 450 samples, slight noise for variability, and a fixed random state for reproducibility. To simplify visualization and analysis, we keep only the first and third dimensions, reducing the data to 2 dimensions while preserving the curve's main structure. The code first verifies that the points data has 450 rows and 2 columns, which is the required format for a 2-dimensional plot. If the data does not match this shape, it raises an error to stop the process. This check helps ensure each point has 2 coordinates and prevents plotting problems later. We choose one point in the dataset as an anchor for comparing nearby neighborhoods. Its position is set to index 225, and its coordinates are retrieved from the data. This lets us study how changing the neighborhood size affects tangent estimation around that point. We choose two neighborhood sizes, 8 and 55, to estimate tangent directions at a point on the manifold. Comparing these sizes shows how smaller and larger neighborhoods can change the tangent estimate. An empty collection is then prepared to store the resulting tangent line segments for later comparison. We test several neighborhood sizes to see how they affect tangent estimation. For each size, we build and fit a nearest neighbors model on the point set, then find the neighboring points around the chosen anchor point. We keep only the neighbor indices, since the goal is to study the local structure rather than the distances. To estimate the local tangent direction, we first select the nearest neighboring points around an anchor point. These points are centered by subtracting their mean, placing the local neighborhood around the origin. Singular value decomposition is then applied to find the main directions of variation, with the strongest direction giving the tangent direction. The first direction from the singular value decomposition gives the main tangent direction at the anchor point. Using a fixed segment length of 1.2, the tangent segment is extended equally backward and forward from the anchor along that direction. The neighborhood size and the segment's start and end points are then saved for later plotting. The notes explain that tangent estimation uses Scikit-Learn APIs to find nearest neighbors, and that the chosen neighborhood size matters. A small neighborhood better follows the local flat region around a point, while a large one may span across the manifold's curvature and give a less precise local estimate. Create a plotting canvas, then draw the manifold points as a scatter plot using their first two coordinate columns. Color the points with a smooth gradient based on the color values and use a consistent point size. Finally, plot the anchor point separately in red with a larger marker, and label it so it can be identified in the legend. The code draws each tangent segment by connecting its start and end points with a visible line. Each line is labeled with the neighborhood size used to estimate that tangent, making it easier to compare how different sizes affect the tangent shown on the plot. The plot is labeled to show that local tangent estimates change with the neighborhood size. The axes represent the first and second coordinates of the S-curve, and the legend identifies key elements such as tangent lines and the anchor point. Displaying the plot allows visual comparison of the tangent estimates on the manifold. This example shows how tangent estimates on a two-dimensional S-curve depend on neighborhood size. Around one anchor point, a small neighborhood gives a tangent that follows the local curve closely, while a much larger neighborhood can cut across the manifold and distort the local geometry. The main lesson is that neighborhood size controls the balance between capturing local structure and being influenced by broader, less local patterns in manifold learning. Eigensolver choices. Choosing the right eigensolver is important in manifold learning because it affects how neighborhood graphs become low-dimensional embeddings. Dense solvers are suitable for small datasets, while large, sparse datasets need solvers that use sparsity to save memory and compute only the most important eigenvectors. This choice influences the embedding's speed, stability, and quality. Choose an eigensolver based on data size, matrix structure, and required precision. Dense solvers are suitable for smaller problems, but become costly as memory and computation grow, while iterative solvers are better for large methods such as Isomap and locally linear embedding, because they target the most important parts of the spectrum. However, iterative methods need careful convergence checks, especially when eigenvalues are close, since they may mix similar directions. In that case, different embeddings may represent valid low-dimensional views rather than solver errors. When choosing an eigensolver, judge it by whether it preserves the reliability of the final embedding. If different solvers produce similar neighborhoods and clusters, small changes in orientation or scale usually do not matter. But If the structure changes noticeably, check the solver choice, graph construction, or dimensionality. Testing several solver settings helps confirm that the learned manifold is trustworthy. Python code eigensolver choices. Compare different eigensolvers for the same manifold embedding, since the solver can affect both speed and numerical stability. If the resulting embeddings are similar, the result is likely reliable. We import key Python tools for generating, reducing, visualizing, and comparing data. NumPy supports numerical array operations, while Matplotlib creates plots. Scikit-Learn provides an S-curve dataset generator, locally linear embedding for dimensionality reduction, and pairwise distance calculations to compare the resulting embeddings. We generate a synthetic, three-dimensional S-shaped dataset using Scikit-Learn's make S-curve function to test manifold learning methods. The dataset contains 450 samples, with a small amount of noise for realism, and a fixed random state ensures the same data is produced each time. The function returns the sample coordinates and a color value that can be used to visualize the points. The code first verifies that the points data has the expected shape, 450 samples with 3 features each. If the dimensions are different, it raises an error to flag the problem early. This check helps ensure the data is correctly formatted before the rest of the code runs. We configure locally linear embedding to reduce high-dimensional data to a 2-dimensional manifold. Using a dense eigensolver and 12 neighbors per point helps preserve local structure, while a fixed random state makes the result reproducible. This setup lets us evaluate how well the method captures the data's essential shape in fewer dimensions. We configure locally linear embedding with the ARPAC eigensolver to reduce the data to 2 dimensions. Using 12 neighbors helps preserve local manifold structure, and a fixed random state makes the results reproducible. This setup supports comparison of ARPAC with other solvers for manifold estimation. We fit a locally linear embedding model to the dataset to map the original points into 2 dimensions while preserving the data's manifold structure. We do this once with the dense eigensolver and once with the ARPAC solver, so we can compare how the 2 methods affect neighborhood relationships in the transform space. We compute pairwise distance matrices for both the dense embedding and the ARPAC embedding, using Scikit-Learn's pairwise distances function. Each matrix records the distance between every pair of embedded points. These matrices let us compare how well each solver preserves the relationships among points in the original dataset. The distance matrices from the 2 embeddings are flattened into 1-dimensional arrays, so they can be compared directly. A correlation coefficient is then calculated between these arrays to measure how similarly the 2 solvers preserve pairwise distances. A value close to 1 means the embeddings are highly consistent in the relationships they capture. The output reports the Scikit-Learn version to support reproducibility, then compares 2 solvers by showing their reconstruction errors rounded for precision. It also reports the correlation between distances in the 2 embeddings, indicating how similarly the dense and ARPAC solvers preserve relationships among data points. A new plotting canvas is created, then a scatter plot shows the first 2 coordinates of the dense embedding. Each point is colored by a data value and given a consistent size. This provides a compact view of the manifold embedding produced by the dense eigensolver. The code adds a title showing that locally linear embedding used the dense eigensolver, labels the 2 embedding coordinate axes, and then displays the plot on screen. This script tests whether dense and ARPAC eigensolvers give consistent results when using locally linear embedding to reduce a 3-dimensional S-curve dataset to 2 dimensions. It compares the pairwise distances in the 2 embeddings and uses their correlation to judge whether the solvers preserve similar neighborhood structure. The script reports the Scikit-Learn version, reconstruction errors, and correlation value, then shows the dense solver embedding as a colored scatter plot. Transforming new data. Transforming new data with manifold learning is difficult because methods like Isomap and locally linear embedding are built around a fixed training set. Unlike principal component analysis, they cannot directly map a new observation. Instead, the new point must be linked to nearby training points so its position in the embedding can be estimated. This works best when the new point lies on the same manifold and its nearest neighbors represent that structure well. For new data in manifold learning, the point is usually added by relating it to nearby training points. In locally linear embedding, its neighbors in the original space guide where it should appear in the lower dimensional embedding. In Isomap, the point is connected to nearby graph nodes and positioned using estimated distances. Both approaches work best when the new point's local neighborhood accurately matches the learned manifold and is not strongly affected by noise. Out-of-sample testing in manifold learning helps reveal weaknesses that may not appear in the training data. A model can map the training set well, but behave unpredictably on new data, especially in sparse or complex regions. For reliable use, transforming new data should be treated as both a diagnostic check and a deployment step, with careful attention to neighborhood size, distance measures, and graph connectivity. Python code. Transforming new data. Transform new manifold data by comparing how familiar and unusual points fit into the learned structure. Use neighbor distance as a warning signal, since larger distances can indicate that a new point may not match the pattern seen before. We import key Python libraries for generating, analyzing, and visualizing data. NumPy handles numerical arrays. Matplotlib creates plots, and Scikit-Learn provides machine learning tools. From Scikit-Learn, we use an S-curve data generator, locally linear embedding for reducing dimensionality while preserving local structure, and nearest neighbors for comparing new points with the training data. We create a small curved training dataset using Scikit-Learn's make S-curve function, which generates a three-dimensional S-shaped manifold. The dataset contains 500 samples, with a small amount of noise added to make it more realistic. A fixed random state ensures the same data is produced each time the code runs. We define 3 new points to test how the learned manifold transforms data. 2 points come from the training set, so they should behave like familiar examples on the manifold. The third point, with coordinates 0, 3, 0, is deliberately chosen to be off the manifold and unlike the training pattern. Each point is given a simple label, so the transformation results can be identified and compared later. Before fitting the model, the code verifies that the training data and new data have the same number of features. If they do not match, it raises an error to prevent an invalid transformation. This check helps ensure the datasets are compatible before processing continues. We fit a locally linear embedding model to the training data to reduce it to 2 dimensions while preserving local neighborhood structure. The model uses 12 neighbors for each point, the standard embedding method, and an automatic eigensolver. After fitting, the transformed training data provides a compact 2-dimensional representation of the data's essential structure. New data points are transformed using the locally linear embedding model fitted on the training data. This places them in the same lower dimensional space, using the manifold relationships the model learned. As a result, the new points can be compared consistently with the training data and analyzed in relation to the existing manifold structure. To estimate how close new points are to the training manifold, we fit a nearest neighbors model with 12 neighbors on the training data. For each new point, we find its nearest training points and average the distances to them. This mean distance indicates how typical the point is relative to the training data, with larger values suggesting it is farther from the learned manifold. The code first reports the Scikit-Learn version to support compatibility and reproducibility. It then prints a simple table showing each new point's mean distance to its nearest training neighbors. By listing each label with its rounded mean distance, the output makes it easy to compare how far the new points are from the training data and spot possible outliers. The plot is created with a figure and axis. Then the training embedding is shown as a scatter plot, using its first two components as coordinates. Each point is colored according to the training color values, using the Viridis-Kohlmarp to show variation across the original manifold. The points are kept moderately sized and partly transparent, so overlapping areas remain visible. The scatter function in Matplotlib is used to plot the transformed new points using the first two components of their embedding as the x and y coordinates. The points are given distinct colors, made larger for visibility, and shown with X-shaped markers so they stand out. A label is also added so they appear in the legend as transformed new points. For each new embedded point, the plot adds its label at the matching X and Y position. This annotates the transformed points directly on the graph, making them easier to identify with a small, readable font size. The plot is formatted to show that locally linear embedding depends on nearby training examples. Its axes are labeled as the first and second embedding components, and a legend identifies the plotted elements. The visualization is then displayed so the training data and transformed new points can be compared. This example shows how a locally linear embedding model maps new points after learning an S-curve manifold. The model reduces both the training data and 3 new points to 2 dimensions, then compares each new point with its nearest training neighbors. Points similar to the original manifold have smaller average neighbor distances, while the off-manifold point has a larger distance, showing it fits the learned structure less well. The final plot marks the new points separately to show how the model places them in the reduced space. In this lecture, you learned to explain the manifold assumption through visual examples, apply Isomap and LLE family methods to nonlinear datasets, and analyze neighborhood construction, solver choices, and out-of-sample transformation behavior. In the next lecture, Lecture B, we will go over spectral MDS TSNE.
Thank you for your attention. See you all in the next lecture.